Alright, geometry students, this video is going to show you how we kind of make connections between different concepts in math, especially geometry, and as it pertains to trig and trigonometry, and where trigonometry is going to go for you in future math classes. So this isn't something that we're going to assess you on. However, it's a really nice connection that we make from previous material to what we're doing now to what you might be doing in the future. So at the top of this page is directly from our special right triangles notes, where you guys figured out and we discussed that in a 45-45-90 triangle, the legs would both be the same, and if we knew one of the two legs, we could find the hypotenuse simply by multiplying by root 2. Okay, and then in a 30-60-90 triangle, our kind of base was the side across from the 30-degree angle. That was what we kind of based everything else off of. If we knew that one, the side across from 60 was whatever that was times root 3, and then the hypotenuse was whatever this was times 2. Okay, and that was our special right triangles section, and this is how we found missing side lengths using special right triangles. Now, we're going to do that, but then we're going to kind of extend off of that. So, this first example here says find the missing sides of these triangles using our knowledge of 30, 60, 90 triangles. So let's look at the first one, A. We're given the side across from 30. That usually makes things easy for us. All right, so looking back up top, if the side across from 30 is our base, then the side across from 60 is whatever that is times root 3. So that would make this 10 root 3. And again, looking back up here, 2 times the side across from 30 would be the hypotenuse. Well, 2 times 10 is 20. All right, fantastic. In B, we're given the hypotenuse. Well, we can use this as if this is twice as long as the side across from 30, divide this by 2. This would be 7. And then this side is whatever the side across from 30 is, times root 3. So 7 root 3. All right, so now that we've done that, we get a little bit of the extension here and how we're going to connect this to trigonometry. So you're asked to find some trig ratios here. Let me zoom out a little so we can try to get this all on the same page here. Okay, so we're asked to find sine of b, basically all of our trig ratios. So we've got ABC here, we've got triangle ITR here. Okay, so we'll do sine of b. Sine is opposite over hypotenuse. Here's b, opposite 10. Hypotenuse 20, this simplifies to 1 over 2. Sine of t, here is t. Opposite 7, hypotenuse 14, 7 over 14. Simplifies to 1/2. Cosine of b. Here's b, cosine is adjacent over hypotenuse. So we get 10 root 3 over 20. How would we simplify that? Well, we'd simplify just the 10 over the 20. 10 divided by 20 is 1 over 2. We still have that root 3 on the top. We get root 3 over 2. Cosine of t, that's adjacent over hypotenuse. 7 root 3 over 14. 7 over 14 simplifies to 1/2. We still have the root 3 on top. We get root 3 over 2. Sine of c, opposite over hypotenuse. 10 root 3 over 20, again is root 3 over 2. Sine of r, opposite over hypotenuse. 7 root 3 over 20 is root 3 over 2. Cosine of c, adjacent over hypotenuse, would give us 10 over 20 or 1/2. Cosine of r, where's r? There it is. Adjacent 7, hypotenuse 14. 7 over 14 equals 1/2. As you guys can see, there should be something interesting that is happening here, and maybe this is where we're going to make the connection. So what can we conclude about the values of sine or cosine of 30-degree and 60-degree angles? Now remember that we got these values from 2 different triangles altogether, and these triangles had different sizes. Yet what we saw was the same values for these cosine and sine ratios kept coming up. So let's take a look here. Why did we group these together, the b and the t? Well, right here, b and t were the 30-degree angles. And why did we group c and r on top of each other? Well, that was because c and r were the 60-degree angles. And what we've seen is we can make some conclusions here. okay, if B and T are both 30-degree angles, which they are from above, and sine of B and sine of T were both 1/2, then maybe sine of all 30-degree angles are 1/2. Okay? Now, why would that make sense? Well, it would make sense. Let's look back up here. Okay? Let's take the sine of this 30-degree angle here. This is all general. We don't even have actual values here. We just have variables. This is the general 30, 60, 90 triangle. And even on the general one, if we do sine of 30, which is opposite A, over hypotenuse 2A, well, wouldn't that also give me 1/2? So we can actually take out this maybe part. Say sine of all 30-degree angles, the ratio of the sine of any 30-degree angle, no matter how big the triangle is, would always be 1/2. Cool. How about cosine of our 30-degree angle here? Okay, cosine of B and T, our two 30-degree angles, were both the same. So maybe cosine of 30 degrees is always root 3 over 2. Well, let's check it out on our general triangle here. Cosine of 30 degrees would be adjacent over hypotenuse. Well, that would be a root 3 over 2a. Well, what happens is the a's would cancel again, and we'd be left with root 3 over 2 generally. So if this is true on the general triangle, without the specific value, it has to be true for every 30, 60, 90 triangle. And again, we can take away this maybe, that cosine of 30 degrees is always root 3 over 2. Okay. Now for similar reasons here, okay, we could go back to our 30, 60, 90 triangle and prove these as well. But as you see that these are the 60-degree angles, so sine of C, a 60-degree angle, sine of R, a different 60-degree angle in a different triangle, both came out to be root 3 over 2. So sine of 60 degrees would equal root 3 over 2 always. And then cosine of 60 degrees would equal 1/2 always, as you see over here, where we have cosine of our two 60-degree angles in two completely different triangles end up coming out to the same ratio. Okay? These are very important pieces of information for you moving forward. Okay? Now we'll make an even bigger connection here. Okay? We talked at the start of our trig unit about how sine of some angle and cosine of 90 minus that angle, its complement, would have to be the same. Well, 30 and 60 degrees are complementary angles, and sine of 30, cosine 60 are the same. Cosine 30, sine of 60 are the same. So this all connects back to everything that we've talked about with SOHCAHTOA. It makes connections with 30, 60, 90 triangles. Okay? And we'll make that final connection a little later in our notes. Okay, but this is the conclusion we found by simply taking two different sized 30, 60, 90 triangles and then saying, wait, maybe this is always true. All right? And just like every mathematician in history that has created some sort of theorem or concept that you now see in a geometry textbook or your geometry teacher teaches you, when they had an idea, they said, maybe this is true all the time, just like we did. Well, what they did is they came back and said, well, let's just think of this generally, and if it's true generally, which it was, now we know it's true all the time. Okay? We'll do something similar for a 45, 45, 90 degree triangle. Okay? So 45, 45, 90. Let's take a look at B first. That's the easy one. Leg 8, other leg 8, hypotenuse 8, root 2. Okay? Now we have the hypotenuse as 10. So remember, we would set 10 equal to our a root 2 side. We'd divide both sides by root 2. We would get 10 over root 2. We'd multiply top and bottom by root 2, so we rationalize. We'd get 10 root 2 over 2. This simplifies to 5 over 1, so we know that each one of these would be 5 root 2. Okay, and that's our knowledge of special right triangles. That's from a long time ago. Let's find some ratios. Let's see if something similar happens with our 45, 45, 90 triangles. All right, sine of O. opposite over hypotenuse, 5 root 2 over 10. That would be root 2 over 2, because the 5 and the 10 would simplify to 1/2. All right, let's take a look at the other triangle. Sine of y, the other 45-degree angle, 5 root 2 over 10, root 2 over 2. Cosine of O, 5 root 2 over 10, which is root 2 over 2. Cosine of y, 5 root 2 over 10, which is root 2 over 2. Now let's take a look at this triangle. Okay. A, also a 45-degree angle, opposite over hypotenuse, 8 over 8 root 2, which simplifies to 1 over root 2. And if we wanted to rationalize this, we'd multiply the top and bottom by root 2, and we'd get root 2 over 2. You can trust me that we would get the same thing for every one of these values. Okay? Doesn't matter which 45-degree angle we're working with. Doesn't matter whether we're working with the this triangle BOY or triangle ABT. Every single value is root 2 over 2. What can we conclude? Well, maybe sine of 45 and cosine of 45 will always equal root 2 over 2. Maybe that's the case. No matter how big or small the triangle is, if we're starting with a 45-degree angle, we take opposite over hypotenuse, or we take adjacent over hypotenuse. When we simplify, that ratio will always be root 2 over 2. Maybe it's true, maybe it's not. Maybe we go back to our general 45, 45, 90 triangle and see if we can prove that. So we've got a root 2. That's our general 45, 45, 90 triangle. Let's just take sine of this 45-degree angle down here. Well, that's opposite over hypotenuse, a over a root 2. If we simplified this, the a's would cancel. We'd get 1 over root 2. We'd multiply top and bottom by root 2, and we'd get root 2 over 2. Cosine of 45 degrees. Let's take a look at this angle. Well, opposite and adjacent in a 45, 45, 90 triangle are the same. They're both the same value, so this should come out the same. We'd get a over a root 2 again, which is 1 over root 2, which rationalizes to root 2 over 2, and we can now cross out this maybe. Sine of 45 and cosine of 45 are exactly the same, and they always will be. Now, where is this going? This is going to what we call the unit circle. All right. In pre-calculus, you'll learn about this unit circle, okay? And it deals with sine and cosine and trig values of all these different types of angles, more so from 0 as we go around a circle, okay? But the most important part is knowing, so we're basically putting a circle on a coordinate plane, okay? And the radius of this circle is going to be 1. That's why we call it the unit circle, okay? So if the radius is 1, this point right here would be 1, 0, because it's a length of 1 from the origin. And this point here would be 0, 1. Okay? Now what we talk about with the unit circle is that there's all these degree measures on the inside, and there's 3 of them that we really want you to know. We want you to know the 30-degree angles, the 45-degree angles, and the 60-degree angles, and their sine and cosine values. And you'll learn that cosine is kind of the horizontal part of each one of these points, the x-coordinate. Sine is the vertical part of each one of these points, the y-coordinate. And the first time we teach it to you, you'll see these values come back in play. So 30-degree angle, if we look at the front, 30 degrees, sine was 1/2, cosine was root 3 over 2. 45-degree angles, both sine and cosine were root 2 over 2. And 60-degree angles, sine was root 3 over 2, cosine was 1/2. And this is something we expect you to remember and be able to refer back to once you get to pre-calculus. And what we've done today is connect your special right triangles to the fact that sine and cosine of 30, 45, and 60-degree angles will always be these same ratios.